Ever get that feeling like we're missing a piece of the puzzle when it comes to, you know, the universe? Well, today we're diving into a theory that throws out some pieces and says, hey, what if our universe exists inside a black hole?
It's a fascinating concept, one that has, intrigued physicists for decades. And recent observations from the James Webb Space Telescope, particularly its exploration of early galaxies, have breathed new life into this idea.
Yeah, we've got a curated selection of research and articles to guide us through this, and we're going to help you navigate all the complexities and, really grasp the potential implications of this theory.
Indeed. It all starts with the James Webb Space Telescope, or JWST for short, peering into the depths of the early universe, observing galaxies so distant they formed just a few 100 million years after the Big Bang.
And that's where things get a little strange, right? I mean, it's not just that we're seeing these early galaxies, it's how they're behaving. That's really turning heads.
Precisely. The JWST's JADES survey, which stands for the Advanced Deep Extragalactic Survey, examined 263 of these early galaxies. And the unexpected finding: a significant majority, around 66%, seem to be rotating in the same direction, clockwise.
That's a huge departure from what we'd expect, right? I mean, shouldn't the direction of galaxy rotation be pretty random?
Absolutely. In the standard model of cosmology, there's no reason for a preferred direction. It should be a roughly 50-50 split between clockwise and counterclockwise rotations. This observed bias, which is actually strong enough to be visible even to the naked eye in the images, challenges that fundamental assumption.
Okay, so enter black hole cosmology, which, as I understand it, suggests that our universe is like nestled inside a black hole, existing in a larger parent universe. Is that a fair summary?
That's the core idea.
Mhm.
Physicists Ranj Pathria and I.J. Good were among the first to propose this concept. And while it might seem like something straight out of, science fiction, it offers a compelling framework for understanding some of the universe's biggest mysteries.
Okay, you've got me intrigued. But how does a universe in a black hole scenario explain this odd synchronized spin we're seeing in those early galaxies?
It all hinges on the nature of black holes themselves. Think about how matter collapses into a black hole. Instead of being like a complete end, what if this collapse is actually a bounce, a transition to an expansion phase, much like the Big Bang? If that expansion occurs within a rotating black hole, it could impart a preferred direction of rotation to the galaxies forming within it.
So if we imagine our universe inside this rotating black hole, it's like the spin of that parent black hole is somehow influencing the spin of the galaxies within our own universe.
That's the essence of it. The idea is that the initial conditions of our universe, including the distribution of angular momentum, are shaped by the properties of the black hole from which it emerged.
It's almost too big to wrap your head around. But if this black hole cosmology is correct, are there any other clues, like other observations in the universe that might back it up?
That's where it gets even more interesting. This model could potentially eliminate the need for some of the more perplexing concepts in cosmology, like dark matter and dark energy.
You're talking about those mysterious forces we can't directly observe, but have had to theorize to explain how the universe behaves?
Right.
Like the invisible scaffolding holding it all together.
Exactly. Black hole cosmology offers a way to explain cosmic expansion and the large-scale structure of the universe without relying on these hypothetical entities. It essentially says that the properties of space-time within a black hole itself could account for the observed phenomena.
So instead of adding these unseen forces into the equation, black hole cosmology suggests that maybe our understanding of gravity and space-time needs a rethink, and that those revised laws of physics could explain what we're seeing.
Precisely. It challenges us to consider the possibility that what we perceive as dark matter and dark energy might be emergent properties
No.
of a universe embedded within a black hole, rather than separate fundamental forces.
That's a pretty radical shift in perspective. But before we get too swept up in this black hole universe idea, we have to acknowledge another possible explanation for this curious galaxy rotation pattern, right? Something to do with how we're observing these galaxies from our vantage point here on Earth.
Yes, you're referring to the Earth's motion effect hypothesis. It suggests that our planet's movement through space, particularly in relation to the cosmic microwave background radiation, could be skewing our observations of these distant galaxies.
So it's not that these galaxies are actually spinning in a preferred direction, but that our own motion through space is creating the illusion of a pattern where there isn't one.
That's the core argument. It's like looking out the window of a moving train. The scenery appears to rush past in a particular direction, but that's a consequence of our own motion. not necessarily an intrinsic property of the landscape itself.
Okay, I'm starting to see how our perspective, even on a cosmic scale, can potentially influence what we observe. But how does this Earth's motion effect specifically tie into the JWST's findings?
Well, the JD survey field is located near the galactic pole. This is significant because the Earth's motion through space is not perfectly aligned with the plane of our galaxy. This misalignment, combined with our planet's movement relative to the cosmic microwave background, could create a subtle bias in how we perceive the rotation of galaxies in that particular region of the sky.
So it's like our planet's unique trajectory through space could be acting as a kind of cosmic lens, distorting the way we see these distant galaxies and their rotation.
That's a great way to visualize it. It's a reminder that even with incredibly powerful telescopes like the JWST, we can't escape the limitations of our own perspective. We have to account for the fact that we're observing the universe from a moving platform, and that motion can introduce subtle biases in our data.
This is fascinating. So we have two potential explanations for this unexpected pattern in early galaxy rotation. On one hand, we have the mind-bending idea that our universe is nestled inside a spinning black hole. On the other hand, we have the possibility that our own planetary motion is creating an illusion of a preferred direction. Where do we go from here? How do we even begin to untangle these two possibilities?
It's a bit like we have these two pieces of a jigsaw puzzle, and we're trying to figure out which one fits into the bigger picture.
Yeah.
You know? To differentiate between these two explanations, we really need more data, more observations from the JWST, and further analysis.
So we need to look for additional clues that could tip the scales in favor of one theory over the other. What kind of clues would we be looking for?
For starters, we need to expand the scope of our observations. The JD survey, while groundbreaking, only covered a relatively small patch of sky. If the observed pattern of galaxy rotation is truly a result of our universe residing within a spinning black hole, we should see evidence of it in other regions of the universe as well.
So we'd need to find this clockwise bias in early galaxies across a much wider range of observations, like a consistent cosmic fingerprint.
Exactly. Finding a similar bias in distant galaxy clusters located in completely different parts of the sky would strengthen the case for black hole cosmology. Conversely, if this pattern is confined to a specific region, it would lend credence to the Earth's motion effect hypothesis.
That makes sense. Are there any other telltale signs we could look for?
Another avenue of investigation would be to examine the properties of these early galaxies in more detail. If our universe is indeed embedded within a black hole, the dynamics of galaxy formation and evolution might be subtly different from what we'd expect in a standard cosmological model.
So we're talking about looking for specific anomalies in how these galaxies are structured or how their stars are distributed, something that sets them apart from galaxies that formed later in the universe's history.
Precisely. We might find the distribution of mass, the types of stars present, or even the way these galaxies interact with each other exhibits unique characteristics that can be attributed to the influence of the parent black hole.
Okay, so by studying these early galaxies in greater detail, we might uncover subtle clues that point towards a black hole origin. That's pretty incredible. But let's switch gears for a moment and dive deeper into some of the implications these theories have on our understanding of the universe. We briefly touched on dark matter and dark energy earlier. If black hole cosmology is correct, it could potentially shake up our understanding of those enigmatic concepts, right?
Absolutely. Dark matter and dark energy are cornerstones of the current cosmological model. They were introduced to explain discrepancies between observations and theoretical predictions. For instance, galaxies rotate faster than they should based on their visible matter, suggesting the presence of unseen dark matter providing additional gravitational pull. And the accelerating expansion of the universe points towards a mysterious repulsive force we call dark energy.
But these concepts have always been somewhat elusive, haven't they? Like trying to grasp shadows in the dark.
That's a fitting analogy. Despite decades of research, we haven't directly detected dark matter or dark energy. We only infer their existence from their gravitational effects. Black hole cosmology, however, offers a tantalizing possibility. What if these phenomena aren't separate entities, but rather emergent properties of space-time within a black hole?
So instead of invoking these invisible forces, black hole cosmology suggests that maybe we need to revise our understanding of gravity and space-time within a black hole, and that those revised laws of physics could explain what we attribute to dark matter and dark energy.
That's the core of it. Imagine a fish living in a pond. It might perceive currents and eddies as like invisible forces pushing and pulling it around. But from our perspective, we understand that these movements are simply the result of the water's flow patterns. Similarly, what we observe as dark matter and dark energy might be consequences of the unique space-time geometry within a black hole.
That's a powerful way to visualize it. So black hole cosmology, in a sense, redefines the playing field. It suggests that these missing pieces of the puzzle might not be missing at all, but rather manifestations of a deeper reality we're only beginning to glimpse.
What about the Hubble tension? You mentioned earlier that black hole cosmology might have something to say about that as well.
Indeed, the Hubble tension, as you know, refers to the discrepancy between different measurements of the universe's expansion rate. One method, based on observations of the cosmic microwave background radiation, gives us a certain value for the Hubble constant, which represents the rate of expansion.
And the other method, based on measurements of distances to relatively nearby galaxies, yields a different value, right?
Precisely. And the difference is significant enough to be considered a genuine problem, suggesting that something is amiss in our understanding of the universe's expansion history.
And how does black hole cosmology enter the picture? Well, one of the intriguing aspects of black hole cosmology is that it doesn't necessarily require the universe to have a single uniform expansion rate throughout its entire history. Remember, we're dealing with a universe embedded within a black hole, a region of space-time with extreme curvature and gravitational effects.
So time and space might behave differently inside this black hole compared to the outside. Could that lead to variations in the expansion rate that we perceive from our vantage point within it?
That's the idea. The way time flows and space stretches within a black hole can be radically different from what we experience in our everyday lives. It's possible that these differences could manifest as inconsistencies in our measurements of the Hubble constant.
So black hole cosmology, by introducing a more complex and dynamic picture of the universe's expansion, might offer a way to reconcile these conflicting measurements and potentially resolve the Hubble tension.
That's one of the avenues researchers are exploring. It's still early days, but the prospect of finding a solution to this long-standing cosmological puzzle within the framework of black hole cosmology is certainly exciting.
It's almost like black hole cosmology is acting as a universal solvent, offering potential explanations for some of the most perplexing mysteries in cosmology. But we also have the Earth's motion effect hypothesis to consider. Does it offer any insights into these larger cosmological questions, or is it primarily focused on explaining the observed galaxy rotation pattern?
The Earth's motion effect, while a fascinating hypothesis in its own right, primarily addresses the observational bias issue. It doesn't offer a direct solution to problems like dark matter, dark energy, or the Hubble tension.
So, in a sense, it's a more localized explanation, focusing on how our own motion through space can influence our perception of the universe.
That's a fair assessment. It highlights the importance of considering observational biases and the limitations of our perspective when interpreting cosmological data. Even with the most advanced telescopes, we have to be mindful of the fact that we're observing the universe from a moving platform, and that motion can introduce subtle distortions in our measurements.
It's a humbling reminder that even as we strive to unravel the secrets of the cosmos, we can't fully escape the constraints of our own existence. We're part of the universe we're trying to understand, and that inevitably shapes our perspective. But this discussion has also brought to light another intriguing question. If our universe does reside within a black hole, what does that mean for the very fabric of reality, the nature of time and space itself? It's a question that really sends you tumbling down the rabbit hole, doesn't it? If our universe is tucked inside a black hole, what happens to our, familiar notions of time and space?
It's where the theoretical rubber meets the mind-bending road. One of the defining characteristics of a black hole is its extreme warping of space-time. Time as we understand it becomes incredibly distorted near a black hole's event horizon.
The event horizon being that point of no return, right? Where gravity's pull is so strong that not even light can escape.
Exactly. Now imagine our universe existing on the other side of that event horizon, inside the black hole. The way time flows within our universe might be drastically different from how it flows outside, in the parent universe, if you will.
So someone observing our universe from outside the black hole, hypothetically, of course, might perceive time within our universe as moving incredibly slowly, almost frozen.
That's one possibility. And conversely, events that take eons to unfold in the parent universe might appear to happen much more rapidly from our perspective inside the black hole. It's a consequence of the extreme curvature of spacetime.
It's enough to make your head spin. Does this distorted sense of time have any implications for how we understand the age of our universe?
That's a question that has cosmologists scratching their heads. We traditionally estimate the age of the universe based on the observed redshift of distant light, assuming a relatively consistent rate of expansion. But if time itself behaves differently within a black hole, those calculations might need to be revisited.
So the universe might appear older or younger than we think, depending on how time is flowing within the black hole compared to the outside. It throws a whole new wrench into the concept of cosmic chronology, doesn't it?
It certainly does. And it's not just time that gets warped. Space itself is stretched and distorted within a black hole. Our familiar three-dimensional space might be embedded within a higher dimensional space inside the black hole, with dimensions we can't even perceive.
That's where my brain starts to melt a little. So we're not just talking about a universe contained within a sphere, but potentially a universe folded and twisted within dimensions beyond our comprehension.
That's the kind of territory we venture into when we explore black hole cosmology. It challenges our fundamental assumptions about the nature of reality. It's a realm where our intuitive understanding of space and time breaks down.
It's both exhilarating and a little terrifying, isn't it? This notion that our entire universe, with its vastness and complexity, might be just a tiny pocket within a much grander and stranger structure.
It's a humbling reminder of how much we still don't know. But that's the beauty of science. It's a process of continually pushing the boundaries of our knowledge, confronting the unknown, and embracing the possibility that the universe might be far more wondrous and bizarre than we ever imagined.
Speaking of wondrous and bizarre, the implications of our universe existing inside a black hole don't stop there, do they? What about the idea that every black hole within our universe could be a gateway to another universe?
Ah, yes, the concept of nested universes. If our universe can exist inside a black hole, then it stands to reason that the black holes we observe within our universe could themselves harbor other universes, potentially with their own unique laws of physics and physical constants.
So it's like a cosmic Russian nesting doll situation with universes within universes within universes, each one potentially branching off and evolving in its own unique way.
That's one of the mind-boggling implications of this theory. It suggests a level of interconnectedness and complexity that is almost beyond comprehension. It paints a picture of a cosmos where the boundaries between universes might be blurred, with black holes acting as bridges between these realms of reality.
It makes you wonder if there's some ultimate parent universe at the top of this cosmic hierarchy, or if it's just universes all the way down, an infinite cascade of realities nested within one another.
That's a question that might forever remain beyond our grasp, a mystery that tantalizes our imagination but might ultimately defy our ability to answer. But even if we never unravel the full extent of this cosmic tapestry, the very act of exploring these ideas, of contemplating the potential for universes beyond our own, expands our understanding of what's possible.
It's a journey that challenges our perceptions and forces us to rethink our place in the grand scheme of things. It's a reminder that we're part of something far grander and more intricate than we can fully comprehend. So where do we go from here? What are the next steps in exploring these mind-blowing concepts?
The quest for understanding continues. The JWST and future telescopes will provide us with more data, allowing us to refine our models and test the predictions of black hole cosmology. And perhaps one day we'll uncover definitive evidence that confirms or refutes this extraordinary theory.
Until then, it remains a realm of speculation, a playground for our imaginations, and a testament to the boundless mysteries that the universe holds. And on that note, we'll leave you with one final thought to ponder. If our universe is indeed nested within a black hole, what implications might that have for the ultimate fate of our universe? Could the evolution of the parent universe influence our own cosmic destiny? Food for thought as you contemplate the vastness of it all. Thanks for joining us on this deep dive. Until next time, keep looking up and keep those questions coming.